Hi everyone. Today is our third lecture, network security. So maybe only today we're gonna start see real stuff. So in the second part of the lecture we're gonna talk about this, which is one known algorithm. So we're building up. So I hope that you're doing well in the homework, and I know you sent me questions to check out. I have to. Maybe you saw my note that in in 2 weeks we're gonna have your midterm, your first exam. We'll be finishing with almost half of the book. All right, no, quiet, but we'll give you early exam. Okay, make sure you're on the track. And then after that, I will switch to the other book for a few lectures, and then come to this book. All right, sounds like a plan. All right, any questions? All right. Alright, so today we'll introduce you to modern symmetric key ciphers. So we'll talk today, usually if we need to talk about ciphers, we could divide the word in two words, symmetric and asymmetric, public key and private key. Alright, so we'll talk about symmetric key, modern block cipher, encryption, where we have a block of data, and we encrypt it as a block. Alright, so n block encrypted with a key will give you another cipher, another n block, n bits block. Alright, but it's encrypted. So we'll talk how this will work. So basically you start with usually with the n-bit plain text. Could be 64 bits, it could be 128, it could be any block. Okay, some of the algorithms tell you what is the size of a block. Some of the algorithms or some of the techniques, it's up to you. Then you have encryption. All right. When you encrypt it, you're gonna get a different n-bit cipher. All right. And when it goes to the destination, it will go and will be decrypted with a decryption algorithm, but both encryption and decryption will use the same key. Just one key. For that, before you do the decryption process, the key must be shared. The key must be shared in a secure way. Remember last time when we spoke about like about algorithms, we said, all right, the algorithm is not secret. So the algorithm used, you know it, everybody knows it. What we have to keep secret is the key. Key must be secret. The strength is that how, first of all, we have to keep the key secret, and how the algorithm is strong that you cannot break the key. So the question is, if you are using with n blocks, these blocks has to be equal. So if you have a block short, let's say that you are using 64-bit block, and the block is short, so what do you have to do? Padding. You have to add dummy bits to the block to make it 64, for example. So that's the first step, is padding. So here example says that if you have a message which has 100 characters of 8-bit ASCII, okay, used, okay, and the block size is 64. So how many padding that you need? So basically what you have to do is the length of the message plus the length of the pad. It has to be 0, not 64. All right. So you have to add certain length to the message. So to solve this question, the pad size will be -800, not 64. That means we have to add 32 bits to this this message, right? To have it 64. So you could have multiple blocks of 64. All right. All right. So substitution or transposition. Last time we spoke about two techniques, substitution where you substitute different values, or transposition where you switch the allocation. So both are used in the modern cipher. Both are used. So the modern block cipher can be designed to act as both substitution and a transposition. Substitution and transposition. All right. All right. So the resistance, you know, to protect it from the excessive search or brute force, we need to, you know, we'll explain in a second. All right, so here another example says, suppose that we have a block cipher of N64. So the blocks are 64, 64, 64, right? And if there is 10 ones in the ciphertext, how many trial and error tests does Eve need to do to recover the plain text from the intercepted ciphertext in each of the following cases? A, okay, the cipher is designed as a substitution, only substitution. So how much? So when you have a block, okay, 6 to the power, the block that has 64 bit. So how many options you could have for this data? 2 to the power 64, right? So how many times you have to try to get the right packet, the right text? 2 to the power 64, right? 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 You have 64. You have a 3 bits block. How many options you have? 2 to the power 3, which means
0 to some.
2 to the power 3, how much?
8.
8, right? If you have like a block 64, how many options? 2 to the power 64. So for a brute force, how many times you have to try it? 2 to the power 64 times. All right, that's for substitution. If you have transposition, okay, in the second case, Eve knows that there are exactly 10 ones in the plain text. Eve can launch an exhaustive search, in fact, using only those 64-bit blocks that have exactly. So it will be much effort to try to figure out the text if you are using only transposition, because there is that. Anyways, so definitely substitution is much more stronger and much more needed, but transposition always needed. Anyways, let me skip this. Okay, a transposition block Cipher model as a permutation. So in here, what we have a 3-bit input and you have 3-bit output. All right. A 3-bit block transposition cipher. So how many options you'll have? 6, right? As you see it in here, the total options. So the first option is the 1 goes to 1, 2 goes to 2, and 3 goes to 3. The first option, input output. What is the second option? Okay, 1. Okay, 1 goes to 1, 2 goes to 3, and 3 goes to 2. So you have 3 combination, which means like 6 options. You have 6 options. All right. So for full size key substitution, in here, show the model and the set permutation tables 3-bit block substitution. So if you look in here, if you have 3, okay, you have the input is 3, so the decoder is the output. So you're changing the 3 to 8 outputs and 8 object permutation. Okay, you have a key, 16 bits for example, permutation, and then you'll the 8 will be changed to 3. Yeah, to 3. Okay, so how many options you have in here for this permutation? 8 discrimination, which is whatever 40,000 different options. All right. So when you have transposition, when you make the permutation bigger, okay, or the size of the block bigger, the options will be, or the domain of the option will be much bigger, right? Okay, that would be much more harder to guess by the attackers, right? All right, so a full-size key n bits transposition cipher or a substitution of block cipher can be modeled as a permutation, but their key sizes are different. Okay, so anyways, so for a transposition, the key size will be log 2 to n discrimination. All right, so let's take a look at the boxes, the P boxes. Okay, P boxes or permutation boxes, which is which kind of cause like transfer for data, from value to value. It could be keyed and not keyed. So there is three, and that's what we call a P box. Okay, a permutation box. All right. There are three types. The first one is a straight box. Straight box. So what is a straight box? That you have, for example, 5 inputs and you have how many outputs? 5 outputs, right? Okay. So there's a map in here. There's a map inside it. So for example, input 1 will go to where? To 4. Input 1 goes to 4. Input 2 goes to where? To 1, right? So this is what we call it straight. So what's a straight box? What's a straight box? Straight box. No, you have to know. Look there and you tell me right now. So what do you have in the straight box?
1 to 1.
Huh?
1 to 1.
1 to 1. All right. So it's like 5 inputs. How many outputs you have? Okay.
One.
Now I did not explain the compression. You have to explain the compression for me. Take a look. It's just English, right? So what do we have in the compression? Okay, which means it's not random input. We compressed. We have 5 input. We compressed it to 3. So 1 goes to 1, and 2 is gone. Okay, and the 3 goes to 2, and 4 goes where?
Go.
Gone. And 5 goes to
3.
3. We compressed. So what is P box? Inputs and outputs. The straight one, we have 5 inputs, you're gonna go to the output. Every input we're gonna go to the output. We'll have output, but it's our mixed map. Right? Alright? Compression, we compress. So is the straight one invertible? Is the straight one invertible?
Yes.
Is invertible, right? How about the compression? The compressed one. Is it invertible? No. Because I lost already, right? I lost 2 values. How can I convert them back, right? Alright? They are not invertible. Let's take the third one. Alright?
Inputs and outputs. 3 inputs and 5 outputs.
So in here, it's expansion box. Expansion box. What's expansion box?
Inputs are less and outputs will be high.
We expand. Alright, so how we expand? Where is the data coming from?
Same inputs are
You see, for example, in here, the 1 went to pin 1 and to pin 4. Okay, pin 4. Okay, the question, is it invertible?
Yes.
Is it invertible? Who says yes?
Just
You say yes. I say no. Because how I know? I mean, when I need to know what goes to 1 in here, how can I know it's this or this?
Should be the same.
Why it should be the same? This is one part of the whole process. There's a lot of things gonna happen. So the data in here might be changed, right? It's like stages. Go from a stage to stage to stage, right? Right? There's a difference. So not necessarily. Alright? Alright. Okay. So I see some people are not awake with me. I can ask a question. You're good. You're good. I guess you're good, right? Okay. You're good. So you're here to why you are sitting in the back? You like it? You like it? Okay. All right. My job as a professor to help you. And the easiest thing for me to keep going. All right, if I see it, okay. My job is to try to take your attention. Okay. All right. All right. Okay. All right. We'll move on. Okay. So before I move on, I just want to make sure everybody's awake. All right. So for P-box, what does P-box stand for? Permutation box. All right. We have three types. What are the three types? Straight, compression, and expansion. What are we using these for? For encrypt. I thought for packing some pizza or something. That's true, for encryption. All right. So for confusion and diffusion, we'll learn about it. So the data is like keep changing, right? We need to change the data, mix it like a blender. Okay, we keep blending the data, changing the data until. All right. Okay. So that's good. All right. All right. So in here, when you see in here, what you see in here, you'll see the figure shows 6 all possible mapping of a 3 to 3 P box. First of all, this is expansion, straight, or compression? Straight. Thank you so much. It's a straight. So these all the possibilities. This all the different possibilities for the permutations, right? So this is, did it do anything? Did it change anything? No. 1 goes to 1, 2 to 2, 3 to 3. How about this? 1 to 3, 3 to 2, and 2 to 1. Okay? This all the possibilities. So if I have 3 inputs, what are the number of possibilities I have? 3 discrimination, which is 3 times 2 times 1, which is 6 options, which is, you can see it right there. So this is an example of permutation table for a straight box. Straight box, a big straight box. So what does it say? It says this is a straight box. All right. And remember, when you're using in here, we don't use like small boxes anymore. We use big boxes. Okay. So what does this box? What is the size of this box? This count. I don't know. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 15, 16, 64. That's correct. 64. Okay. So if I have the input 64 bits, this will be output. How can I read it? So what is the bit? What will be the bit? What will be the output? Where is the output of the first bit coming from? Where? From which pin? From 58. So the 58 pin, the 58th pin input, gonna go to where? To the first. Okay. How about the 64 output comes from where? From the 7th. So the 7th input will be connected to where? To the 64. How do I know this is 64? 1 to 16. 17 to 32. 33 to whatever to 64. Right? So that's the box. So you could always represent the box in as a table. As we'll see in a second. Okay? Alright. Okay. So it says in here, design an 8 by 8 permutation table. Okay, 8 by 8 permutation table. Okay, for a straight P box that move the 2 middle bits, which is bit 4 and 5, in the input word to the 2 ends. What are the 2 ends? 1 and 8. All right. So that means what means? Look in here. Means okay, 1 and 2 and 3 and 6 and 7 and 8 will be as they are, but you know the first one, the bit number 4 or the input number 4, we're gonna go to where? To 1, output 1. And bit number 5 will go to where? 8. To the output 8. Where do I have a picture? So in here, this is a different one. So in here we have P box and a P box with N inputs and M inputs. So it's not a straight. It's not a straight. So this is 32 by 24. That means how many inputs I have? 32. How many outputs? 24. Is it a straight? Is it a compression? Yes, compression. All right. In compression, what happens to some of the inputs? Get lost, right? We don't move them. Can you tell me one is lost in here? 8. Where is 8? Do you have 8? No. So where is 8? Gone. Right. All right. So output pin 1. Where is it coming from? From input. Which one? 1. How about 16? Coming from input? 17. Right? 17. I'm not sure. I mean, so if I have like, a box like that, okay, so inputs, right? Okay, inputs. All right, so the inputs, how many inputs I have? 1, or let me put it in 1, 2, 32. This 31, 30. This is 2, 3, 4, 5. And you have output 1, 2, 3, 4. And then here 32, for example, 31, 30. All right. So if I need to draw this, okay, the output 1 coming from where? From 1. So if I draw it, how to be drawn? Like this. 1 connected to 1. Output 2 coming from where? 2. Output 3 from 3. Output 4 21. So somewhere in here we have 21. I have to connect it like that, right? Right? Okay. In here you have example 32, 24. I think that's the same example. And an expansion P box of P box with n inputs and m outputs, where m is greater. So this is an expansion. So 12 and the output 16 is expansion. That means we have multiple outputs. So look at 0, 1, for example. Twice, outputted twice. You see it? Right? Okay? Expansion. You got the idea. Alright. So a straight P box is invertible. We could invert it. But compression and expansion P boxes are not. Alright? And that's very important. We're going to come to this point when we study real algorithms. It's a very important thing. Okay, if it's invertible or not invertible. Okay. Alright. You are in the back. Okay. So this will show you, okay, how inverting is happening. Okay. Can you explain it? Just read and explain it. Tell me.
Want me to explain it first?
Yes. Yeah. And shout, that everybody can hear you.
Inverting the permutation table.
So this is, you're right. So this is the original table, which is 6, 3, 4, 5, 2, 1. Yes. Clever. Okay. Then number 2, what you do?
Swap
You
content.
put, no, here. What you do? Add indices. So 1, 2, 3, 4, 5, 6. Right? Okay. Number 3, what you do?
Swap content.
Swap content. So this swap. So this will go inside and this will go outside, right? So the 1, 2, 3 now went inside, and the 6, 3, 4, 5 went outside. All right? Then what you do? Sort based on the indices. Where's the indices? Okay, indices here, right now. Okay, here. Okay, you sort in here, and the output will be 6, 5, 2, 3, 4, 1 after you sort. So when you sort, what is the first thing gonna go? 6, 2. Right?
Two box around
This is also
Oh, business. Okay, which one?
the
Outside
dominant
the box.
is-
Outside
Okay.
box.
Outside box. Okay, 1, 2, 3. Okay, then what we have? 6, 5, 2, 3, 4, and 1. So that's your input, and that's what? Your output. That will be your output. Okay, how you invert, right? Remember one thing, that all the algorithms we have for decryption and encryption, do we have two different algorithms or the same? Same. But applied reverse. Okay, applied reverse. So we have to be able to invert the processes we are doing, right? All right. So in here, compression and expansion beatbox are non-invertible. Are you convinced with this? Do I have to talk about it? You're convinced they are not invertible, right? Let me move on. Okay. Then let's go about S box. So P box for what? Permutation. S box for what? Substitution, right? Okay, so the S box, substitution box, can be thought of as a miniature substitution cipher. Okay, so let's take a look in here. So, for example, in here, you have 3 inputs, okay, and 2 outputs. You could the inputs, for example, is whatever the x's, the inputs, okay, and you have 2 outputs. So there is like kind of process. You substitute with the value with a process, okay. So the y1, the output 1, it equals XORing x1 with x2 with x3. The y2 is just x1, and you could write it. You could simply write it as like matrices multiplication. So permutation is we don't change the values, we don't do process, just we're switching them around. Substitution, you're really substituting with something, but we substitute with something that means has to be controlled, right? It comes as a result of operation, all right? As a result of operation, whatever. I mean, like in here we said y1 equals x1 XORed with x2 with XORed with x3. It could be anything, right? That's your design. That's your design. You design how you're gonna do the substitution, okay? All right. So in here, the S box with the 3 inputs, 2 outputs, the same thing. 3 box, okay, so Y, 2 outputs, but there's a different process in here. Different process. You could use whatever you want. In here, another substitution, for example. In here, what you're doing, substituting 3 times 2. So the input, so you're creating a table. So the leftmost bit will be the index for the column, and the rightmost bits will be the index for the for the 0 1 here is the index for the rows, and this will be the index, the other 2 will be index for the column. So if the input, for example, 1, as you see, 1 0 0, so what's the output? The intersection, which is 1 0, right? So in here, what we are doing in here, we're substituting, right? How we are substituting? From the table, okay? So in here, so if I have, for example, the input is 0 0 0, so what is the substitution will be? 0 0. So I substitute every 3 bits with 2 bits. If the input is 1 1 1, so I substituted with what? 0 1. Is this an expansion or compression? Compression. It's a compression. I'm substituting 3 with 2, right? So based on the table, an input of 0 1 0. Where is 0 1 0? 0 1 0, which is in here. It will give you 0 1. 0 1 0 1. An input of 1 0 1. Where is 1 0 1? 1 0 1. The result will be 0 0. Simple. Alright? Good. So here we'll try to tell you there's different mechanisms for substitution, right? So the S box may or may not be invertible. May or may not be invertible. In an invertible S box, the number of input bits should be the same as the number of output bits. Alright? So it has to be straight to be invertible. Alright? Okay, same thing in here. And here 3 bits, so S box table for exam, whatever. Okay, alright. an important component in most block ciphers is what? Exclusive OR. Exclusive OR operation. Okay, is exclusive OR invertible or not invertible? Who says yes, who says no? Yes. Yes, I'm sure. Why? Ooh, how? Yeah, but how? What's the condition? There's a condition. It has to be one fixed input, which is the key. Okay. Right? So to have it invertible, x to y and y to x, always the second input has to be the same, which is k. All right? So XOR is a main component we use in all the algorithms. All right? It's exactly also like from all the operations we learned: addition, subtraction, multiplication, multiplication, division. Which one we use the most? Modules, right? Modules. So it's a. Okay. By the way, I hate this. I love this classroom. I hate it because I like to be close to the students when I talk. But the computer is there. I don't know how to solve this problem. I keep walking. So I'm trying to control myself to stay here, but I don't know how. I have to walk. So oh, maybe I could use. I have a clicker. Yep. Maybe that's what I'm doing. Yeah. Good. All right. All right. All right. So an important component in the most block ciphers is the exclusive OR operation, as we discussed before. Okay. Anyways, okay. So it has the 5 properties, which is the closure, okay. So we already learned that from previous. Okay. All right. So now the boxes we learned, they could be keyed or keyless. Key with key or without key, right? Okay, so the inverse of a component in a cipher makes sense if the component represents a unary operation. Unary operation, that means you have one input and one output. Okay, so for example, a keyless P box or a keyless S box can be made invertible because they have one input and one output. Right? So we could use the XOR to make it to make it invertible if we have a fixed key. So as you see in here, okay, this encryption decryption is very easy to switch from X to Y and vice versa if we keep the key fixed. All right. So there is different techniques here we're gonna talk about. Still, we are talking about like possibilities, different techniques. In the following chapter, we'll jump in a real implementation. What they have used. Real means real. Okay. All right. And here another component found in some modern block ciphers is the circular shift operation. I'm sure you have learned about this in DCC. And okay, so basically in here, you have in here before shifting, so you have bits from B0 to B7, and you could have shift left. You could have a shift left 3 bits, okay? And after shifting, what will happen? It will if we shift 3 times, B5, B6, B7 will come to the right side, and this will be shifted. Also, we could have right shift. Could be 3 bits, could be 2 bits, could be 4 bits. It doesn't matter. So here, what it's trying to do, trying to have circular shifting. So if, for example, in the encryption, I'm doing circular shifting for 3 bits. Okay, left shift, for example. In the decryption, what I have to do? Right shift, 3 bits. All right. So is this invertible or not invertible process? Invertible. Okay, that you could invert what you have done. You could also use a swap operation, which is a special case of the circular shift operation. A swap operation, which is a circular shift of the operation. So, for example, the k is n over 2, so we swap the first half to the second half, and the swap operation is very much used a lot, as we'll see in the real encryption techniques. So, is it invertible or not invertible? That's it. So swap back. Swap back could invert what you have done in the first process. All right. Two other operations found in some block ciphers are split and combine. You could split. Okay, so this is split it in half, for example. Okay, and then in the reverse you could combine. So all of this are invertible operations, right? Product ciphers. So Shannon introduced the concept of a product cipher. A product cipher is a complex cipher combining substitutions and permutation. So what's a product cipher? Combines substitution and combination, permutation, and other components we discussed before. There's two things we always have to do, okay, and together must be there to have a good algorithm. The first one is diffusion, and the second one is confusion. Diffusion and confusion. So diffusion hides the relationship between the ciphertext and the plain text. Diffusion. So you'll not be able. So if you have the plain text and you have the ciphertext, you look at this and this, you'll never be able to know what's the relationship. Okay, we'll not be able to know what's the key, for example. All right, that's diffusion. And confusion hides the relationship between ciphertext and the key. Okay, so confusion and diffusion. All right. Also, in quite often, okay, in the algorithms that we use it multiple rounds, not one round. It's not like one P box or one S box. It's like multiple rounds. As a matter of fact, in DES, how many rounds we have? 16 rounds. We're gonna use 16 different keys, 16 rounds, and each round has 3 or 4 operations. So the input goes to one round, output becomes the input for the following round, next round, okay, until to the end. So that will make sure that we do what? Confusion and diffusion. So basically, if you look at the plain text and you look at that ciphertext, has no relation. Okay, it's completely blended. It's exactly like, you know, you have the blender at home, you have 5 strawberries, 1 banana, 1 apple. I haven't seen people put watermelon, but let's say watermelon. Okay, you put them in the blender, you blend them. Okay, and then somebody tells you, okay, get me the banana and give me the watermelon and get the, can you? Can. Same thing in here. Okay, except in here we can, in one case. What's the case? You have the key. If you have the key, okay, you'll be able to do that. All right. So in here, when you see in here a product cipher made of 2 rounds, all right. So in here 8, for example, okay, and that's not a real algorithm, just an example. So you have in here 8-bit plain text. So in here, okay, 8. So this is kind of a straight box, okay, straight box, and this is a key mixer, okay, and the key mixer, what we call it, white noise, okay. So you have the key passed in here, and the output. What is the output? 4 S boxes. 4 S boxes. The output, each S box in here. What is the S box? Substitute box. So 2 inputs, 2 outputs. 2 inputs, 2 outputs. 2 inputs, 2 outputs. Then it goes from substitute box to where? To permutation P box. Okay, P box, right? All of this, what we call this? Round 1. This is round 1. Now, the output of the round, now there is a middle data called 8-bit middle text. Again, it's like 6 bits. We pass it to the key mixer, which is the white one. Again, we have 4 S boxes, and then it goes to the permutation box. RAM 2. So it's like a blender. Give you output, another blender, line, okay, give you output, and this is the 8-bit ciphertext. So if you look at the input plain text and you take a look at the output ciphertext, it will be completely different. All right?
There is no chance that you're gonna come back to the first,
Come back where?
to the first.
The same input? If you do, that means the weak algorithm never used. Okay?
Can the rounds be different? In this case, the rounds are the same.
It's always the same.
Each round is
It's always the same. Some exceptions, like in this, for example, for the loss, we'll see it in a second part of the lecture. So is just to cancel the mixing, the round number 16 could be a little bit different. There's two ways to design it. Okay, but technically the best algorithms, you have multiple rounds, and each round exactly the same. Even when designing the hardware, it will be much more easier to design that because mostly now it's a hardware, right? So that's what it is. All right. So in here, just an example is for that. So basically, I mean, we're talking about confusion and diffusion. If you be kind enough, follow up with me. So start with the plain text in here, the 8, for example, and you have in here you have the key one. So you XOR, for example, the 8 with something from the key. So when you XOR it, will give you some data in here. Is different, changed. Then from S4, which is substitution, of course, the input value substituted with something else, all right? And then what happened? In this permutation box, the bit number 8, for example, went to the 4, and 7 went to 4, I'm sorry, 7 went to the 4, and the 8 went to 2. And then here in the middle text, again, gonna go XORing it with a different key, right? And now, you know, we start from the 8 came where to here 2 to here 4, for example. And again another, okay. So what do you notice in here? What do you notice? That one input contributed to the value of how many outputs? 1, 2, 3, 4. Confusion and diffusion. Okay? So the value of one input contributed to the final value of 4 outputs.
That's
Okay.
not invertible then?
It is invertible.
The
It is.
previous slide says that they have to be the same to be invertible.
They are the same. When you start from here, I mean in here, this is like a silly example, but usually every element as you go up is invertible. So in here, for example, I mean in here for decryption you have the similar thing. Okay, so the input gonna go in here, it will be invertible. We'll see. We'll see a real example in a second.
There was a previous slide that said for it to be invertible, the input had to be the same number of bits as the output.
Where? I mean, in here, you know, in here it's all the same input and output. In here, all the same size. Are you with me? All of them the same size. Yeah, all of them. So in here, for example, the number of inputs in here is the same as the number of outputs. And the same thing in here, number of inputs will be the same number of outputs. Okay. The only thing what we have like a box, for example, 8 by 8. We handed it into 4 boxes, 2 by 2. All right. So we'll see a real example. All right. So the modern block ciphers are all product ciphers, given. Okay. All right, but they are divided into there's FISO and there's non-FISO. Okay, non-FISO cipher or FISO ciphers. I think it's a German word. All right, so FISO ciphers designed a very intelligent and interesting cipher that has been used for decades. A FISO cipher can have 3 types of components. Self-invertible, like what? What is self-invertible? XOR, self-invertible, right? Okay, and invertible. okay, and non-invertibles. Okay, and non-invertibles. All right. So the first, so as you see in here, okay, so you have a plain text, for example, there is a mixer. The mixer will have a key. The key will be passed to a function, whatever is a function. The output of the function, which has the input, the key as input, will be XORed, okay? And you have the C1, the encryption, all right? And that's what we call it, the mixer. So the mixer usually, it combines the key with a function and XOR, okay? And when you reverse it, okay, the C2, the same thing, we're gonna go in here. The same key, you're gonna have the function. Remember, the XOR, what we call the XOR? Self-invertible, right? So as long as you have the same key, you will be able to invert it up. You'll be able to invert it up. Okay. So diffusion hides the relationship between ciphertext and the plain text. Alright, so this is an example, okay, and here, trivial example. So the function extracts the first and second bits to get 1, 1 in binary of, or 3 in decimal. So it's like 1, 1 or 3 in decimal. The result of squaring it is 9, okay, which is, okay, 1, 0, 0, 1. So what we are doing in here, what is the function? Okay, what is a function? So you have the plain text, whatever the plain text, which is 0, 1, 1, whatever the plain text, right? And the function is squaring the key. So you presume here the key is what? Is 11, 1, 1, I'm sorry, which we converted to decimal 3. So 3 squared will be presented as like 1, 0, 0, I mean, 9, for example, presented 1, 0, 0, 1. So this is the 3 squared, and this is the cipher. So when XORing it will give you this result. What is this result in here? 1, 1, 1, 0 is the cipher, is the C. So in the decryption, we put the C, which we got in here. As long as I have the same function, and I'm doing XOR, so this is the output, and this is the output of the function, I was able to get what? The plain text. Alright, one more time. Okay, one more time, a silly example for the function. What is the function in here? Squaring. Squaring the key. Alright, what's the key? 1, 1 binary, which is 3 decimal. Okay, when you square it, it will become 9 decimal. When you write it as a binary, how you write it as a binary? 1, 0, 0, 1. Great. So we have a plain text. What is a plain text? 0, 1, 1. All right. XORed with the output of the function. Give you what?
Cipher.
The cipher. Now I need to give the plain text. How? What should I do? XOR it with the function of the key. Give me back what? The plain text. All right. So XOR, is it self-invertible or not self-invertible? Yes. So, and also in here when you talk about the function could be a complex operation, not as squaring only, simple. It could be a very complex. It could be a sequence of operations. All right, as long as you apply them. Okay. So in here, improvement of the previous Faisal design. All right. So now, in the first Faisal we saw in here what we did in here. Let me go back. So in here we took a plain text as one block. In Faisal, usually they don't do that. They don't take as one block. They divide the block in 2 blocks, left and right. Okay? Okay, so that's what you do in here. So, okay. And what's the point in here? To cause more confusion, right? So, so in here you divide it to the left and right. And what you did, left and right. So you pass all the right to the second round. So right 1 becomes right 2, right? Now, you don't pass the left all the way to left 2. No, you change it. How you change it? With the key going to the function, and you XOR it with the left. So L2 does not equal to the L1. L2 equals what? L1 XORed with the right side after it's manipulated with the function. Alright?
So L2 is equal to L1.
What?
Is L2 equal to
L1 does not equal to L2.
R?
Never. But R1 equals to R2.
This is
So R1 all the way back where? To R2.
this is less secure
What?
because you have half of the messages the same.
Okay, her question is, before we used to put everything in the operation, okay, and here just we are doing the half, right? So it says it's less secure. Okay, so before we used like mix everything. We go back. Okay, before what we used to do in here, you take plain text and then you change it completely, right? And then you have the output. Now what you are doing, you're taking the only the half, okay, and you are changing it, okay, and you're passing the half as this. So it should be less secure. Make sense what she said? I think it makes sense. Right? I think it makes sense, right? So before we took the whole okay. So it's a bit we put it in a different way. You're making a juice, right? Cocktail, right? So you mix the banana with the watermelon with the strawberries. Then you put the apple without mixing, just you put it with it, right? You're not mixing. So will you be able to take the apple later? No. Right?
Even for the L2 you can go back because we already given R2, which is R1, which is used for the function L2. So to get the L2. So it's like you're giving both, like you see.
Yeah, I mean, your question is, okay, it's why R1 is not mixed, all right? Okay, actually no. Why? Because this is 1 gram. When you look at it as 1 gram, here what you said is correct, right? But what will happen when it goes to the next round, there is a switch. No. Usually the left side goes to the right and the right goes to the left. And that will contribute more to the confusion. Okay, so the left will be in the right and the right will be in the left and contribute more in the confusion.
So why, if you know the algorithm, the function seems irrelevant because it's just producing another key, just modifying the key, but they don't know the key, then it just seems like it's irrelevant, the function.
It is relevant. It is relevant because the function is the input to the function is the key.
So I was changing the key to another key.
Okay.
There's still key. And if you know the algorithm, you know what the function is going to do to the key anyway.
But you don't know the key.
Yeah.
And the problem is when you are the hacker, when you try to break a function, you try to break the whole algorithm, either you go from outside or you go from inside. Okay, so if you could do brute force. I'm sorry, brute force. Where is it? Okay, brute force. Okay, and try the key. So what security you could have in here? You have to have large key. So that's so many options to try, right?
Mm-hmm.
Okay. The other thing is you could like trying to go step by step and try to see what happens in here. So basically there is input, data, and output. Try to figure out what has happened. So when you have a complex function with a long key, will make it very hard to deduce. Yes, right?
So in this case, you don't know the algorithm.
You know the algorithm, but again, I mean, you know the algorithm has inputs. You know exactly what's the function. You know it. Okay, but the idea here is not the instant change in here. It's a contribution to the change at the end. Usually, where you start from when you try to break the data, start from where? from the cipher, right? And the key. So if the cipher is completely mixed up, because of all this consecutive operations, will make it harder or easier for you to break? I know you're not convinced, you'll be convinced, okay? As we go on, okay? Alright, so, alright. So in here, what happens in here, okay? So we divide the plain text in left and right, alright? And that's the answer to the question. What we do the next? The right will go here, and left will go in here, and now what was right becomes a left, and it will be mixed. It will be mixed with the function. Anyways, that's how it is. Okay, let me put it this way. That's how it's designed. Okay, so it goes. You have the mixer. You have the switch, the swiper, and you have L2, L3. You're gonna go to round 2. Okay, then when you go to the reverse in here, okay, all right. So you start with allow. You use the keys in reverse. Okay, and by the way, it's not the same key. I forgot to mention that. Key 1 is different than key 2. So there is a whole process. If you have 16 rounds, you have to generate different 16 keys from the main key. So the key is not the same. All right, it's a different 16 keys. All right, and then you go and then reverse the process. So in here you have L3, L3 and R3. Let's say it goes in here. So switch again. Then you run the same operation. It will be invertible. You go up until it gets down the data. All right. So non-feasible ciphers, okay, uses invertible components. Use invertible components only. Okay, we'll talk about it later. So attacks on block ciphers. There is many different attacks in traditional ciphers can also be used to modern block ciphers. But today's block. So for example, one of the blocks is one of the attacks is differential cryptanalysis. So Ailey and Shammer introduced the idea of differential cryptanalysis. Okay, so if you have a chosen plain text example in here, in this example in here you have a plain text with the key give you the cipher. All right. So let's say that C1 equals the plain text XOR with the key, C2 plain text 2 XOR with the key. All right. If you have two ciphers, which is cipher 1 and cipher 2, okay. If you XOR them together, it will equal to the plain text ciphered with the key and the P2 ciphered with the key. That means they are equal to the plain text XOR with the plain text. So for that, you need to have two ciphers and two plain texts. Okay? Okay. You don't have to have the key, right? Because you suppose you try to get the key. So if you have the cipher and the block, the cipher and the plain text, and cipher plain text, so XORing the ciphers, it will equal to XORing the plain text. Okay. From there, you're trying to figure out the key. So we add one S box to the previous example in here. So let's say you have 3 inputs, okay, 3-bit inputs, okay, and in here you have 3 output, okay, and you have the key is 3, so 3, 3, 3. The output will go to substitution box, okay, and that's a substitution box, all right. So the input is 3 bits and the output is 2 bits. How can I know the output? From the input. So if the input is 0, 0, 0, so if it's in here, the X is 0, 0, 0, gonna go here to be 1, 1. If the input is 0, 0, 1, it becomes 0, 0. So it's like a compression box, right? All right. So in the differential analysis, basically you're trying to collect stats, right? So for example, in here, okay, Eve now can create a probabilistic relationship as shown Okay, so if I do plain text, XOR plain text, and the output in here is ciphertext XOR, okay, so what is the size of the plain text? 3 bits. When I XOR them together, how many bits I will have? 3. What is the output? Is cipher, which is 2 bits. I XOR 2 ciphers will give me how many bits? 2 bits, right? Alright. So in here is, alright, what is, okay. So how many options I will have? I will have, like, you know, I mean, how many options I could, you know, for a 3, for example, for 3 bits, how many options I'll have? 2 to the power of 3, 8, right? All right. So the question is, if I have the input, okay, 0, 0, 0, what are, or I'm sorry, if I have the cipher is, if I have the cipher is 0, 0, okay, how many options, or how many, what is the chance? What is the chance that I'll have the input as 0, 0, 0? 100, right? Okay, that means 8 choices, right? 8 choices. All right. If, okay, in here, for example, if I have the plain text 0, 0, 1, okay, I have 25% that the cipher will be 0, 0, and 25% will be 0, 1, and about 50% will be 1, 1. Anyways, I built like a statistical model in here. It's like here, okay? So in here, what does it say? That if you have like the XORing, the plain text with 0, 0, that is 100%, it will be what? The cipher will be 0, 0, right? So, anyways, let me back a little bit. You know, for the attacks or for trying to figure out the keys and all that, it's a lot of the operation is what? Statistical operations, analytical operations, heuristic operations, right? So you have to have a good statistics, you have to good heuristic mechanisms, because, right? That's what they do, right? Okay. Brute force is the easiest one, but brute force, is it smart? Is it smart by itself? No, brute force just you have to have a computer, run it for 200 years, and try and give every key until it breaks, right? But it does not make sense, right? So before you're trying to use brute force, what you have to do some analysis, okay? Some keys, they are not, option. Don't try them. And there is domain, reduce the domain, let's say, of a tribe, reduce the domain. So that's what is basically is differential distribution table. I'm not sure if if I'm able to make you understand it very well, but I'm sure when you read the textbook, you go step by step, okay, you will understand it. I've been teaching this course for many years, and every time I prepare for this class, I have to go to the textbook to go through the steps. It's a little bit confusing, right? Still, if you have questions, come to my office and I'll explain. So in here, the same thing. You're trying to do from the table, do the sum. So it says, for example, let's say C1 equals 0, 0. What are the options for X1? And again, if you are confused, you have to go to the graph in here. Where is X here? Okay, and the C. So X is 3 bits, C is 2 bits. All right. So, okay, it will be like 0, 0, 1 or 1, 1. There's 50% chance either, right? And then you try to try and error, try like different plain text, and come, for example, with what is the value of K in here. So K for the first try came in here 1, 0, 1. You tried another sample and gave you 2 options, for example. It gave you 0, 1, 1, and give you another option which is 1, 0, 1. All right. So from that, what you could know from the 3 results you got, that mostly the first bit of the key is what? 1, because it's 1, 1, 1. Okay, but in here is 0, 0, and 1, the second bit. The third bit is 0, 1, 1. So you kind of, did you sort of, okay, the first bit of the key will be 1, for example, binary 1. Then you could try different, like, combination of P1 and C1, P and C, and try to run the, okay, until you try at least to know 50% of the key, then we'll reduce the domain for you. Am I making a sense? I'm talking, make sense? All right, if I am not able to deliver it to you, I apologize, but, it's confusing, okay? So, anyway, so differential cryptanalysis is based on a non-uniform differential distribution table of the S boxes in the block cipher. A more detailed take a look at that. Then you have linear cryptanalysis, and you know what's cryptanalysis, right? There's cryptography and cryptanalysis, right? All right. You can take a look at that. Okay. So the modern stream ciphers, okay, what's stream ciphers? Okay, that you are encrypting like as you go, bit by bit. So there's a block. We were talking so far about what? Block ciphers. We divide the data. So which one is better? Which one is faster? The stream ciphers. Okay. So basically, as you go in here as a stream cipher, you have like multiple keys. The key will be generated. It's not like a fixed key shared, it will be generated as you go. So for example, to encrypt P1, you have to have key 1 encryption, P2, key 2, and so on and so forth. So in the modern stream cipher, each R-bit word in the plain text stream is enciphered using an R-bit word. An R-bit word in the key stream to create the corresponding R-bit. Anyways. We'll have real examples later when we advance in the course, okay? So basically, in short, it could be synchronous and could be asynchronous. Synchronous and asynchronous. In synchronous stream cipher, the key is independent of the plain text. It's completely independent, okay? It's independent. In asynchronous, it's generated from the plain text or from the cipher. So like, let's say you already encrypted something, okay? Already encrypted. I need to have another key for the next one. I'll generate the key from the previous cipher. It's like a chain.
Does that expose the relationship then?
Hmm?
Does that not then expose the relationship between the two? If you don't keep them generated?
Sure, you have to use. So it's like, it's, I mean, it will be clear when we start explaining, in chapter 9 or whatever real applications. But basically, let's say that you have P2, P3, right? To encrypt this, you have to start, for example, with key, this K1, right? All right. So I have to have a key in here. Okay, I have to have key 2 to encrypt P2. But where's key 2 coming from? From C1, for example. So some part of C1. So I cannot get key 2 until I get what? C1. All right. So I use C1 to generate the key for the next. In this case, what I have to share? Only the first key. The first key, which is key 1, where I started. And then it goes in sequence. All right. So we'll go CR4. Okay. So in synchronous, random sequence bit generator. So it's independent from the data. That's independent. Okay. So PI, KI, BI plus 1, KI plus 1, and we'll continue. Okay. Again, here we don't have blocks. We encrypt as we go, stream, like streaming, right? Okay. Examples for it is the FSR, the feedback shift. What time is it? All right. I'll leave it for you to take a look at this. You could take a look at this at home. Well, let me explain it quickly. All right. So in here, what you do for generating the key. So in here, the idea in the string is you as you go, what you do, generate the key. All right. So look at the LFSR. Okay. So you have like the base B0, B1, B2, B3. Okay. And what you do, okay, you do operation between B0, B1, XORing and shifting, and the P4 becomes in here and keep shifting, right? Keep shifting. So every time, with every click, what you are doing, you're generating what? A different key. Okay? If you want to look at this in table, that's what it is. So you start with, you can put here, with the base. What is your base? 1, 0, 0, 0, okay? And what is the P4? It's the result of XORing what? P0 and P1 only. Okay, let's go forward. So what will be the value of P4? 1 XOR with 0. What will give you? 1. So what you do is shift, right? The P4 will go, the 1 goes in here, the 0 goes in here, the 0 goes in here, the 0 goes in here, the 1 goes in here. So what I generated now? The first key, all right? Then now, P0, B0 and B1 will be XOR. What's the value? 0. Then shift, 0 goes in here, 1 goes in here. So now I generated what? The second key, and so on and so forth. All right? So what I'm doing in here, this is just one technique for generating a key. Okay? All right? Anyways, so you could take a look at. Alright, so let's have a break for 10 minutes and then we'll go to the real life. We'll talk about this. Alright? If, I know it's like intense. I mean, network security is not easy course. Okay, it needs background, it needs some math, it needs some focus, alright? And just go through the material chapter. I promise you'll understand by yourself because it's easy if you go step by step. If still you have confusion, please come to my office. I'll spend not 5 minutes with you, 50 minutes to go step by step with you if I have to. Okay? All right? And plus, when you do the homework, it will help you a lot. How is the homework, by the way? I forgot to ask. It's good? Is it too long? Is it long?
Yeah.
Okay, how many hours it takes from you?
1 hour.
1 hour? That's good? That's good. All right. All right, so by the way, a lot of the questions you see them in the exam. Okay? So if you do, then you'll be happy in the exam. Maybe. All right. All right, so let's go to DES. Okay? So DES was created, just a second, let me change this. Okay? So this was created in 1973. NICE published a request for proposals for, and by the way, I mean that's most of the algorithm. That's how it started, like the announcement for proposal, request for proposals, and then they get evaluated, and then they get adopted. Anyways, in March 1975. A draft of the Federal Information Processing Standard, the FIPS, was issued. Anyway, so this is a block cipher. What does mean a block? I mean, let's say, like we divide the word usually in 2 words. So we have a block cipher and we have stream ciphers, right? And we have public encryption and private encryption. So in the public encryption, how many keys we have? 1, shared between the sender and the receiver. In the private encryption, how many keys we have? 2. One is public and one is private. Let's forget about that. Let's forget about that for now. So now DES. What is DES? Is it a block or a cipher? Is it a block or a stream? It's a block cipher. Okay. Is it a public or private encryption? Public. That means we need how many keys? 1 key. Is it Feistel or non-Feistel? It's Feistel. Okay, it's Feistel. What does mean Feistel mean? That it uses self-invertible, invertibles, and non-invertible components, the three of them. Just explained that in the previous lecture, right? Alright, so basically, okay, it's a block cipher. What's the size of the block? 64 bits. Okay, so the block has to be 64. If I have 1 million bits, what should I do first? I have to, yeah, check how much pad I need, but I have to divide my data, or 64, 64, 64, 64, and the last one it might need padding, right? All right. Now, what is the size of the key? 56 bits. 56 bits, right? All right. So that's what we need to know so far. All right. So the encryption process is made of two permutations, key boxes, which we call initial and final permutations. Initial and final permutations. All right. So the general structure of this as a following. Okay. All right. So we start with the key. What is the key size? 56 bits. Actually 64. Actually 64. But the 8 bits are for what? For parity. For parity. The real key, what is used, the real key is 56. And from the 56, how many keys are going to generate? 16 keys. Why 16 keys? Because they have 16 rounds. The key of each round, what's the size of the key of each round? 48 bits. So I'm going from 64, remove the parity bits, to 56. And then from 56, I'm going to 48. How many keys? 16. All right? All right. Good. So we start with the initial permutation and the final permutation. Okay? So how many bits are the input for the initial permutation? 64 bits. How many output for the final permutation? 64. And these two boxes invert each other. They are the invert of each other. Simple? So if there is nothing in between them, okay? If there is nothing in between them, that means the input will go to the output the same place. One goes to one, two, two, okay? If you combine the two boxes, they invert each other. Fair so far? Fair? All right. All right, and then in between, we have how many rounds? 16 rounds. We have 16 rounds. All right? All right, so let's take a look at the initial and the last. Where is the initial? You see the initial where? That's the initial and the last, okay? And let's assume there is nothing in between them. So if you look at the initial and the final permutation, okay, it's like it's a box. It has 64 input, 64 output, and designed in a certain way. Who designed it? The people who created the algorithm. They decided, for example, pit 1, for example, input 1 goes to where? 40, right? And 58 goes to where? To 1. You see the 51 goes to 1. All right? All right? So if I move the 1 in here, you see the 1 in here goes where? To 58. Okay, so 58 goes to 1, 1 goes to 58. That means they are what? Inverting each other. Right?
Is this always fixed with that permutation?
Fixed.
Everybody
Fixed.
knows that, and
Everybody knows that, including my mom and my dad, if they know security. Google is the same thing. All right? The only problem, the inputs and the inverting, but of course the output will be completely different. Why? Because you see the black thing in here? It will do a lot of confusion and diffusion. Right? So far, so it will be a very nice project. Now, basically now you know every single box in this algorithm, how it works. You get to know how the input, how is the key work generated, step by step, and how is the output. The best project I could give to you is what? Just write a Python code for this. Right. Okay, I will not do that because I did not do that myself yet. Alright? whenever I try to give a project or something, I try, okay, but my point in here, it's not a joke, my point is, if you would like to write the DES, which has been used for so many years, maybe still being used, you can do that. It's there, step by step, as we'll see. Okay? Alright, so the description of these boxes, the yellow boxes, are there. What are the inputs and outputs, okay? So usually how we write these boxes? Like this, okay? So in here, for example, okay, the output for the initial permutation, the first output, coming from where? From 58. Did we see it in here? You see the 58 goes to where? You see it? In here, the 58, let me go to the mouse. The 58 in here, you see it? Do you see my mouse, by the way? Is there a mouse moving? Oh. Okay, the 58 in here goes to where? To 1, right? So basically, this box, the first box and the second box, that's the map. Alright? Is it easy to program? Very easy to program. Alright? The location on the matrix tells you the output, and the number on that location tells you what? The input. So that's very easy to program. It is a very easy thing to do. Same thing with the final permutation. So they invert each other. Done? Are we done with 2 boxes so far? Done? Clear? Okay. Alright, so these are examples how to invert. I already showed to you. So basically in here, when you try, for example, find the output of the initial permutation box when the input is given as, so what is this input? It's a hexadecimal. Hexadecimal. So what you have to do, you have to convert it to what? To binary, alright? And you'll find only bits 25 and 64 that have ones. Alright? So look at the bottom one actually. Look in here. Start looking here. So I did that myself too this morning. I tried to make it here. So this is in here, for example. Let's say it's input or output. So each one of these is what? A hexadecimal number. So if you need to convert the 1 to a binary, how many bits you need? 4. 4, right? So that means the first bit is what? 1. The rest is here. The first, so this one, you see this one? The 4 in here are there here. 4 plus 4 plus 4 plus 4. So the first bit is 1. When you look at this in here, which is here, it's in here. Okay, so this is the 4 in here. So that means bit number 15 is what? Is 1. So we start counting from 1. It's not 0, I'm sorry, 1. 1, 2, 3, 4, until what? 64. Alright? So you convert the hexadecimal to, and you know where is the ones. Okay? And then, anyways. Alright, the initial and final permutations are straight P boxes that are inverses of each other. They have no cryptographic significance in this. And nobody knows why they put them there. Alright? So there is, I mean, the authors or the people who created the disk put them there. Okay? There is few guesses why they put them there, but nobody for sure know why they are there. They invert each other. Okay? That's a fact. Okay. Alright, so when you go to the DES, uses 16 rounds. Each round of DES is a Feistel cipher. So basically, the inputs, what is the input? What's the block? 64 bits. What we do, we divide it in left and right. 32 and 32, right? In here. I'm here. Okay, 32 and 32, left and right. Okay, so what we do with the right? It goes all the way to where? To the left. Can you see it? It goes all the way. You see the right? It goes all the way to where? To the left. Becomes the left, right? And how about what will happen to the left? It will be XORed. XORed in here, XORed with what?
Function.
XORed with what?
Function.
XORed with the right, with the output of the function, and the input for the function is the first key, the round key, with the right side. So we'll take the right side with the key of the round, we do the function, the output will be XORed, and the output will go where? To the right. So whatever was right become left, and what is left become right. Alright? And this is one round. This is one round. So, right? So this is a swiper, and this is the mixer. Alright? And we have the bits in top. Which parts we don't know so far. We don't know what's happening. We don't know what is the function. We need to know what's the function, what's happening inside the function. Swiper is easy. You spot swiping, right? And we need to know how the key generated. The key generated from where? From the 56 bits. And we generated how many bits? 48. We need to know how generated, right? Okay, and we need to know also what is the function, what is inside it. What does it do exactly? So let's go on. Okay? So it's like every block we know exactly how it's designed. Alright? We don't know why sometimes, why they choose, for example, this box, you know, why one goes to 58 and 40 goes, well, no, they designed it this way. Okay? And I mean, like, there's a lot of analysis. Okay, so let's go to this function. So where are we now? The function in here. You see the function in here? So let's go inside the box. So the heart of the disk is the desk function. The desk function applies a 48-bit key to the rightmost 32 bits. So it has two inputs. The function has two inputs. What are the inputs? The right part of the data and the 48-bit key. Alright, so what will happen to the 32-bit first? The 32-bit will go to expansion box. Expansion box. 32 bits becomes how many bits? 48. Then the 48-bit will be XORed with what? With the 48-bit, and will give you how many output? How many bits in the output? 48 bits. These 48 bits, we're gonna go to the 8 S boxes. How many S boxes? 8. So that means each one has how many? 6, right? 6, right? Alright, 6. And each one of these S box has the inputs, 6 inputs. How many outputs? 5. The S box has 6 inputs and 5 outputs. So 5 times 8, how much? 5 or 4? 4 maybe. 4 outputs. I'm sorry, 4. 4 times 8, how much? 32. So I started from 32 bits. So far I'm 32. And then there is a straight P box will give me a 32. So for this function, what's the input? Half of the data. How much half of the data? 32 bits. Alright. And what is the other input? The key. What's the size of the key? 48. So what I do with the 32? Expand it. 48 and 48. What I do with the key 48 bits and with the data 48 bits? It's order. Then what I do? I divide them into 8 S boxes. The X box is expansion or what they call it, the compression. Expansion or compression, right? So it compresses from 6 to 4, alright? Why we are doing all this? Alright, 4. Then, okay, 6 to 4. Okay, so the total will be 32 bits. Then we have a straight P box. Alright? So now what do I need to know? Which boxes I don't know how they are built. I need to know the expansion box, how it works. I need to go inside it and see how it works, right? And I need to know what else also. I need to know each one of these S boxes, how it work. They are compression, right? 6 inputs, but how it work? Pin 1 goes to where? Pin 2 goes to where? Okay. And all the 8 are different, not the same. Everyone has its own rule, its own map. And then I need to go inside this straight beatbox and know how it works. Good? All right. And still, I have to know how I generated the key, round key. Good. So let's just start with the expansion beatbox. How many we have? We have 8 of them, 32 bit input, and which one? Oh, this is the expansion. We're talking about this expansion in here, right? Okay, 32. We have to get how many? 48. So I have 8 of them. So I have like in here 4 give me 6, 4 give me 6, and 4 give me 6. Anyways, so I'm changing from 32 to 48. And how I'm doing it is very simple. Okay, so very simple. Okay, so the first bit coming from the last one. Okay, and the last one coming from where? From 1. Okay, and this will go down, go down, go down, 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 down. Okay, and the first one for the next one comes from the last of the previous one. So it's like swapping, 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 swapping. That's enough. The authors of this desk did it this way. Okay, did it this way. That's how it's spelled for many years, right? So now we expanded it from 32 to what? To 48 with a very specific. Can you program this? Can you design a hardware to do it? Easy, very easy. You know how it works, right? So again, let me refresh your memory. What I'm talking about? I'm talking about which area? This one is now this one. Clear? Guys in the back? All good? All right. So although the relationship between the input and output can be defined mathematically, this uses table 6.2 to define the beatbox. Okay? So this one is defined like this. Okay, table. So if you need to write a program, Python program, just you have to apply this. So clear? Okay, so this is for the first box, second box, third box, and the 8th box. Alright? So we moved again from here. This is the here, and you present it as a table. I don't think there's anything, you know. Then we go to the whitener. What is the whitener? When you see whitener, always the XOR, right? So after the expansion happens, what we're gonna use, we do the XORing. Then after that, we'll have the S box. Where is the S box? Let me go back, just to refresh your memory. Okay, where is it? The S box. Where is the S box we're talking about? Here. How many S boxes we have? 8 of them. So let's take a look at that. Okay. So these are compression, right? The inputs are 6 and the outputs are 4. That's why the total inputs are 48 bits and the output is 32 bits, right? So basically, how can I find the value? They created for you 8 tables. Okay, 8 tables. This table has 4 rows and 8 columns. So you have 6 bits, right? Okay. You take the first 2 bits and that will be the row number. So if you have 2 bits, how many options you have? 4. 4 rows. And you have 4 bits, how many options you have? 8. So that's exactly what you do. So So you take this is coming from bit 1 and 6, I'm sorry, 1 and 6 will tell you the row. And the middle bits will tell you what? The column. You take this value, that will be the output.
So every S box has a different table?
Every table, yes. So we'll take a look in here. So this is, for example, S box 1. Well, I don't have it in the PowerPoint slides. So this is box 1. If you look at your textbook in here, so there is a box for each S box table. Okay, so this starts S box 1. Okay, 2, 3, 4, 5, 6, 7, 8. Okay, who populated this data? The builders of the desk. Why they put this data? I don't know. Okay, okay, that's how okay. So basically that's what it is. So this one. So for example, okay, if for example let's say that the 6 bits are like this. Let's take example 0, 1, 1, 1, 0, 1. 1, 1, let's say. So for the row, what I have to use? 0, 1. And for let's make it simple. Say 0, 0, 0. And for the column, what I have to use? 1, right? So 0, 1, 0, 1, which is 1 in here. And 1, what's the value will be? 15. So I have to write 15 in 4 bits. In 4 bits, right? That will be the output. So I converted 6 bits to 4 bits. All right? All right? So we converted the 4 bits. That's the output, the 4 bits. All right? Then we have the straight box. Where is the straight box? We go back. That's a straight box. Okay, the straight box, the input's like 32 and the output is 32. Straight box. Alright? And that's the map for the straight box. So the output for the pin 1 comes from where? Input 16, right? Alright? The output for pin 32 comes from where? Input 25. Clear? Okay? So let me go back to our figure in here. So now, did I cover all the boxes? So we covered this, how it works, right? XOR is an XOR. Then the 8 X boxes, we have the tables for this, we covered them, and the straight, right? So if I ask you to write a code for all of these boxes, can you?
Yes.
You can, because you have all the data. What's remaining in here? The key. So far, the key. How the key is generated. Are we still friends? Good. I know end of the lecture that your energy goes down, you get hungry, and you might So if you have a question, just ask. All right. All right. So in here, so that's what we do. If you look at this cipher and the reverse. Okay, things will go, will go round, until the last round, then it goes in here, and then we'll go. We reverse, we use the keys and reverse. So this should be, a simple thing to do. All right, let's talk about the key generator. So that's how we generate the keys, right? I'm not sure if it's clear, can you see? Okay, so we said, how many bits we have for the key? 56. Actually, when you receive the key is like 64. 8 are what? Parity for the accuracy, right? 8 are parity, right? So the real key, how much? 56. All right. So look at the top of there. Okay, so the key, so 64. So it says parity drop. So we have remaining how much? 56. The 56, what we do, we divide it in two. So how much each side will have? 28. 28. 28 gonna go to the shift left and both. We're gonna go to shift left. Alright, so what's the shift left?
3.
Circular shift, right? Alright, how many times they shift?
1.
How many times they shift?
3.
Sometimes one time and sometimes twice. How can I know? From the table in here, can you see the table in here? It says if it's round 1 and 2 and 9 and 16, shift one time. Otherwise, you have to shift how many times? Twice. So, if this is like the first round, how many shifts I have to shift?
1.
1. If it's the 16th round, how many times I have to shift?
1.
1. If it's the 21st round, how many times I have to shift? I think
Yeah.
There is no 21st.
there is no 21st, right? Thank you. Good. All right? Good. So, again, we have the input at 28 after shifting one time, 28 shifting one time. And then what we're going to have? A compression P box. And the output of this compression P box will give you 48 bits. So what is this? The first key. The first key. It's in here. You see it? The first key in here. Where goes the first key? So the first key goes to where? To the first round. Alright? We'll continue the data. Gonna go in here. Another shift. This is round. What is this round? 2. How many shifts I have? 1. And I'll do compression again and key 2. Then you go to the third. How many shifts I will have? 2 shifts from the table. And then I have the third key. I keep going until the last one. I have the round key 16. So now exactly I know how can I generate the key. Alright? I know how to generate the key. I know how to generate and design every box in the algorithm. You agree? Anything is missing? Right? Everything is okay. So that's basically this. That's what it is. This. And this is the parity bit drop. Okay. And this is the number of shifts. So for example, is in round 1, round 2, round 9, and round 16 is 1 shift. Otherwise, 2 shifts.
So the parity bit drop, that looks like a permutation table.
I mean, like the computer go to that.
Parity
Okay.
bit drop table.
The 64, there is certain, so for example, the bit number 8, number 16, number 24, number 32, okay, the 8 bits, okay, these all parity bits will be dropped.
Look at the order.
Yeah, I think so.
The orders are different than 1, 2, 3.
Let me check. So for example, look at this in here, the parity drop, which one is missing? Do you see 08? So that was dropped.
But the order.
That's right, I mean, they dropped and rearranged in a certain
So
way.
like a permutation table.
Yes, yes,
Compression permutation.
yes, yeah. All right, but 08 is done. 16, do you see 16 in here? No. 32? No. 24, is there 24? No, exactly like what I told you. So the 8, the 16, the 24, the 32, these are particles, they are dropped. And then structured in a certain way, in this way. Okay? So basically, if you look at the table, how many bits we have, how many here? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. So 7 times 8, how much? 56. After dropping the particles. Okay? There's the key compression table and all. Okay. Alright. So basically, let's take this example, okay? We choose a random plain text block and a random key. Okay, the block is how many bits? 64. The key how much? No, 56. Okay, 56, right? Okay, so look in here, if you look at the plain text, and look at the key, and look at the ciphertext. So can you see any relationship between the plain text and the ciphertext? Completely different. Completely different. Alright? And that's not the most important thing. The most important thing is the avalanche effect. That means if you change one bit in the input, in the plain text, the cipher has to be completely different. So it's not like you change one bit in the plain text and one bit will be changed in the ciphertext. It's everything, at least like 28 bits changed. The more bits changed, that will mean the more secure algorithm.
So you could calculate all 16 bits at the beginning of the program, it's just going to be used for all the text, the same 16 bits. Those don't change throughout the. So you have the text coming in blocks of 64,
Yeah,
but the 16 keys are going to be the same for the next block of
it will
64.
be different. Every key is different.
The 16 keys are different,
Different, yes.
but they're the same for all 60, for each 64 blocks coming in. So you do the first 64 words,
Okay.
whatever. You're going to use the same 16 keys. The next 64 words are going to use the same 16 keys, right? It's all dependent on the initial keys, not dependent on the text.
It will depend on the confusion, because we did the confusion and diffusion, right? Okay. So this is a good example. Maybe that will answer your question. Let's take a look at this, and then you can feel free to ask the question. So look in here what we did. Okay. So I can't see it. I don't know what's going on. Right. So we'll go in here. Okay. So in here, this is your plain text. Okay. Plain text. And this, after initial permutation, gave you this. After splitting the first, okay, initial permutation, now you divide the data to left and right, right? So we just put the left in here and the right in here, all right? And we keep generating the keys, right? The keys completely generated, right? So you'll see, so left will be, I mean, as you go, this will be shifted like this, right? Right? And then this will be shifted like this, shifted like that. When you keep going in here, okay, shift until the end, okay, after the combination of the last two, that will be the output, and the ciphertext, that will be the final ciphertext. So it's completely different. In the next one, what we did, we changed one bit. I'll show you. And that's the reverse, okay. In here, yeah, let's take a look at this. So in here what we have, this is the plain text, all zeros, right? And this is the key, random key, right? Okay. So the ciphertext is this, completely different, right? Completely different. So what we did, we took this plain text and we changed only one bit. We changed only one bit, right? And we'll apply the same key. Look at the output. Completely different. Completely different. Alright? Completely different. So it's enough to change one bit on the key or on the plain text, and will give you completely different ciphertext. Of course, that's in the most of the cases, but over the years, they discovered some weaknesses. For certain inputs, it could repeat the output. And since then, they started thinking to abandon this. All right? They started by securing it by double this and double this. Now, did I answer your question? No. What's the question?
So that was for the first 64 blocks of text coming in.
Yes.
For the next 64 blocks of text, key 1 through 16 are still gonna be the same, because you
No,
gotta
it would be,
the keys themselves.
the keys will be the same because you're applying, okay, so I understand your question. So if you have a very long data, okay, you're gonna divide it into blocks. And you're gonna apply the same
16
key,
keys.
okay,
To each block.
okay. That I don't know. Because my best guess that usually what they do, they apply a different key. So, no, it's the same key because a shared key, shared original 64, yes, so it's the same key, yeah, let's say the same key.
Yeah, so you only calculate the 16 keys at the beginning of the program.
Exactly.
To pass all the data.
Base all the data for that, yes. So where is the mixing coming? The mixing coming, actually the generating the key does not do a lot of mixing, it's only generated 16 keys for you, right? For a, the mixing is coming from all the Beatboxes and is boxes and all of that. That's what the mixing is coming. Yeah. So the question is, what we said, like when you have a long message, you divide it into blocks. The size of the block 64, right? So if we have a sender and the receiver, usually they agree in one key. So you have a sender and the receiver, sender, that's the question. Sender and the receiver, right? So both in a hidden channel, they have to share one key. This key is 56 bits, right? Alright? So basically, every time these two people communicate, they're gonna use the same key. That means, that is a question, that means every time they have to generate the same 16 48-bit keys, right? Alright, so is that a weakness or not a weakness? It's, okay, because you keep looking. So the question is, the answer is, the confusion and diffusion is coming from the whole process happening, okay, and the key is contributing to building the function, which caused the diffusion. Anyways, that's how it's spelled. So this is a very important thing to show you the strength of the algorithm. Okay, so the check of, and this what we call this the avalanche. The avalanche. This one change will change everything. Right? So although the two plaintext blocks differ only in the rightmost bit, the ciphertext blocks differ in 29 bits. Alright? So the ciphertext, the two generated ciphertext, they differ in 29 bits. Out of how much? 64. Okay. So is that very strong? Not strong? Of course. I mean, if you can have more bits of different, that would be stronger, right? This means that changing approximately 1.5% of the plain text creates a change of approximately 45% in the ciphertext. Right? Number of bits differences for the example before. Okay, at round 16 we have 29 bits different. At round 15 we have 30 different, and so on and so forth. Anyways, around 10, 39. At the bottom line, okay, there is an avalanche effect in here. The completeness effect means that each bit of the ciphertext needs to depend on many bits on the plain text. And we showed that from the very beginning, right? So like, you know, you have the final output bit. It was generated by many input bits. Okay, many input bits contributed to it. And this is clear from the S box, from the B box, from the number of rounds, that it will be clear. Okay, let's take some weaknesses in the Cipher design. So there is some weakness in the S box, some weakness in the B box, and these are critiques happened over year. So for example, in the table in here, the weak keys, there is some weak keys, never use them. Okay, never use them. So for example, the first key before part is dropped, like 0, 1, 0, 1, 0, 1, you know, the first one in here. Can you see it? Alright? So the actual key, the 56 after the dropping will become like that, okay? This also, the actual key will become like that, okay? So these are weak keys. Let us try first weak key in the table, see what will happen. So if we try the first key in here, you see the key in here which is 0, 1, 0, 1, 0, 1, see it? Alright? And we have this plain text, and we'll give you this ciphertext. Okay. If you apply the same key for the cipher I generated in here, what does it give me? Give me the original plain text. So I encrypted the plain text with this key. I took the cipher generated, I encrypted again with the same key. What it gave me? Plain text. Oh my god. This is a big issue. Big issue. Okay? So that's the problem with these weak keys. Okay, this is the weak keys that you don't use in this algorithm. So of course, over the years, I mean, it's clear to you by now the strength of the longer the key, the more stronger the algorithm, right? Okay, at least from the brute force point of view, right? Brute force, you keep trying different keys, right? So over the years, the double encryption and decryption when a weak key. So to solve this problem, you could have like plain text, this cipher, another this cipher, 64. Okay, so now you have 56 plus 56. How many keys you have? 112, right? Okay, kind of 112. And then your inverse cipher. So you could use, a solution that just to make sure. So with that, there is also semi-weak keys or semi-weak keys. They are in here. So if you encrypt with them, look at round 1, round 2, whatever, round 16. You'll see, for example, in the middle, not a lot of changes happen to the data. Not a lot of changes happen to data, and that's not good. Okay, that will be weak. You need to have encryption algorithm that in every round kind of give you like completely different data, average everywhere until the end. Until the end. A pair of semi-weak key also, K1 and K2. I'm going to solve a problem here. I'm going to skip this. So we'll come to the final thing to fortify the this. You could use double this and triple this. I'm sure you heard about double this and triple this. So yes. So you have like this, and you use this again twice. So you have two keys, key 1 and key 2, and you reverse the process. You start with the key 2 and then key 1. So you encrypt, key 1, key 2, and decrypt. Okay. Also, there is triple this, where you like this and 3 keys basically, key 1, key 2, key 3 times you apply it in sequence, and that makes the key how much? The key, it could be like 2 keys, key 1, key 2, key 1 again, or it could be completely 3 different keys, key 1, key 2, key 3, which will make it the most fun. What's the problem like applying it 3 deces in the row? Is there any problem? Don't you think it's like time consuming? Right? Think about like hard disk drive, that you're applying 3 desks on the hard disk drive. Right? Even right now, and if you apply like BitLocker, anybody has BitLocker in his computer? Yeah, right? You have to. You don't guys have BitLocker? No?
What is it?
What is it? It's encryption for your hard disk drive, but I don't blame you because it comes with professional Windows. It does not come with the regular Windows, so I'm not sure what version of Windows you have, or enterprise Windows. But basically your hard disk drive is encrypted. And there's a third party, you don't have to use the Windows. You could buy it or download it. So your hard disk drive is encrypted, completely encrypted. AES encryption. So let's say somebody gets your laptop. I mean, at that time you worry about what?
Data.
If it's encrypted, you don't worry about data. You worry about the $1,000 you just lost. That's it. And anything you could fix it by money is not a problem, right? But let's say somebody gets your computer and you have your picture and your party pictures, photos from your party, from your honeymoon, anyways. Okay, and your laptops, and somebody gets your laptop, what will happen? Problem, right? What if you are a researcher or you are a businessman and you have all your data in laptop and somebody gets your computer? Okay, it will be a problem. So it's a must nowadays. Okay, to encrypt your hard disk drives. Okay, so encryption, when you put BitLocker, I mean, you notice even now it's a hardware, but you notice maybe it's a little bit slower. Why? Because whenever you try to write to the hard disk drive, what will happen? Somebody has to encrypt it for you. Process. Okay, it has to be encrypted, then written to your hard disk drive. When you try to read it from your hard disk drive, what happened? Decryption has to happen, right? So slow algorithms are problems. This is a fast algorithm. Triple disk, that means 3 times, 3 like encryptions and concept. You understand what I'm saying? So nowadays, very few people, I mean, until now you could configure it by the way your computer to use this and triple disk. I think so, alright? But don't use it. Now there is AES, so we'll talk about it later. That's what you use, right? And it's like 256 key. This is only 56 key. This is nothing. Nobody uses it. This is not secure. No government allowed to use this anymore. No government. It's gone. Okay? But it was one of the very first. Now we're talking about larger kiosks and much more secure stuff that you need to worry about. Anyways, I'm not sure what else. Triple this, okay? Then security of this. Okay, the brute force attack. Is it very strong in brute force attack, you think? No, it's a small key, 56 is a small key. Then differential cryptanalysis and linear, I mean, you could take a look at that yourself. Alright, any questions for me? Alright, so I think today is, I mean, we just started to realize what is encryption, right? So started this course talking about like, different things that we need for security, and the major thing is a cryptography, right? A cryptography, okay, cryptography is like converting data to encrypted data, and now from now on, until we finish, we're gonna see real application. One of them is this, but before we start talking about this, think about like we just started. Today is the first class, and we just started explaining this for you. Will it be easy? So we had to start going through like the mathematical, the XOR, the modulo, and modulo is not used much, but we'll use it in different algorithms later. The S-box, the P-box, how they work in general, the Python, okay, all of these things, okay. And now when we explain this to you, it became very clear. And we'll move on. I'm not sure what's next chapter. So, the next one, we're gonna explain the Advanced Encryption Standard, the ES, okay? And that's kind of the standard nowadays, is used everywhere. So, the same thing, we'll explain to you how is it taught. It's much more complex than this. It's, and then after that, if we have time, we're gonna talk about the modern symmetric key ciphers, okay? And we'll talk about how to chain things and outflows. That should be an easy thing to cover. Alright. Any questions? Still friends? Get you tired? Alright. Right, please do your homework, okay? After next week, we're gonna have your exam, okay? So, let me know if you have a question. I have my office hours every Wednesday from 1 o'clock to 6 o'clock. And you could come by and forward me if you have any questions. Thank you so much.